Reddit is home to over 100,000 communities and has over 52 million daily active users. Can you guess how many pieces of content are created on Reddit every year? The answer is about 3.6 billion. However, not all of them are funny memes or healthy discussions. About 230 million pieces of content, that's about 6%, get removed every year for violating the rules of a specific community or one of our site-wide content rules. My name is Fred, and I'm the engineering manager of the real-time safety applications team at Reddit. We keep Redditors safe by proactively identifying and taking action against harmful user behavior and content in real time. I'm joined today by Bhavani and Vignesh, who are both software engineers on my team. If you're watching this talk, then you probably already know what Flink Stateful Functions is. And perhaps you're even excited about it. At Reddit, we're excited about Flink Stateful Functions too. And so we want to share with you how we use it to protect the integrity of our platform and ensure a safe user experience. In this talk, we'll be sharing how we designed and implemented our real-time stream processing platform using Statefun, how we built on top of it to create a good developer experience, and finally, how we are rolling it out to other teams in safety and across Reddit. So, let's dive in. As mentioned just now in the introduction, about 3.6 billion pieces of content are created on Reddit every year. That's a rate of about 114 per second. About 233 million of these, or about 6%, get removed every year for different types of violations. That's a rate of about 7.4 per second. Of those, about 148 million are removed by Automod, or our volunteer moderators, for violating the rules specific to their communities. That's about 4%, or a rate of 4.7 per second. The remaining 85 million are removals by admins for violations of the site-wide rules. That's about 2%, and a rate of 2.7 per second. Naturally, we want to keep the exposure to this type of harmful content as low as possible. You may already be familiar with our reporting functionality on Reddit. If you see a post or a comment that potentially violates a community's rules or Reddit's content policy, then you can report it and it will get reviewed and actioned as appropriate. This function of content moderation works remarkably well. However, one challenge that we face when relying on user reports is that a user is necessarily exposed to the harmful content first before they can report it. But our goal is to ultimately limit that exposure as much as possible to ensure a safe and predictable user experience. While every piece of content is different, most content online has most of its lifetime impressions relatively shortly after its creation. Therefore, identifying and taking action against harmful content proactively and quickly is crucial to reducing exposure. But that's not all. Let's take spam, for example. If a user posts a relevant link in a relevant community, then that's generally a good thing. That stimulates discussion. But what if a user posts the same link in 200 irrelevant communities? Or if suddenly 200 seemingly unrelated users post the same link in different communities, but all from the same IP address? Then that's probably spam. And so I hope this small example shows that violations can be, and typically are, context and state dependent. So what can we do about all of this? How can we try and address it? At a high level, we want to be able to react to events that happen on Reddit in near real time, analyze them, identify violations, and then automatically take the appropriate action. Stream processing is a natural fit for this. The workflow I described can be broken up into separate steps, which depend on each other and together form a data flow graph. The workers implementing these steps each listen to specific messages, for example, on specific Kafka topics, and emit new messages into different Kafka topics, which then serve as the input of downstream workers. Together, all of these workers listening to and emitting new messages implement a large and complex workflow. Now we're at a Flink conference, so let me share why we decided to use Flink and StateFun to implement our system and how we use them. So let me get started by sharing why we decided to use Flink. As mentioned in my example about spam, many different types of violations are context dependent and often also state dependent, so we must rely on stateful logic to identify them. Plain old stream processing, such as queue consumers, don't really support this, whereas Flink is designed for this type of problem. For much of the stateful logic and some of the destructive actions, we also need control over the guarantees the system can provide, such as exactly one's execution. Further, we also wanted to have support for replaying recorded events easily, both for testing and for retroactive event processing. And finally, we also wanted to use a technology that is proven to easily scale out to very large event volumes and very large state sizes. Altogether, that's why Flink was a natural fit for implementing our system. The next logical question would be to ask why we decided to use StateFun. First of all, right now Reddit primarily uses Python and Go for implementing backend services. We therefore wanted to be able to write workers using the tools and the languages and frameworks we already use, and also be able to easily add support for any other languages or frameworks in the future. Preferably, the workers should also be deployed and instrumented like any other RPC type service we already have to simplify operations. And finally, workers should be scaled and deployed independently of the stream processing system components. StateFun supports and enables all of the above and much, much more, so the choice of using StateFun was an easy one. However, deploying StateFun on its own also wasn't quite enough for what we had in mind. First of all, we wanted to have some guarantees around message correctness for different Kafka topics. Meaning we wanted to make sure that only specific workers can actually write to specific Kafka topics and not write to them directly by name. We further wanted to have guarantees that certain Kafka topics only hold values of a certain type, so that the ingresses and egresses, which also can be typed, can be connected accordingly, so that we can ensure that inputs and outputs are always the expected type. Secondly, we wanted to allow different teams to easily collaborate in a multi-tenant environment, so that their workers can interact, but are also as decoupled as possible. And thirdly, we wanted to support several instances of the same worker in different contexts. For example, to replay a stream of recorded events or for integration testing. As a result, we implemented Snooron. Snooron is effectively an orchestrator for and an abstraction layer on top of Flink Stateful. It implements its own data model of sources, workers, sinks, and environments, generates the corresponding Flink and Stateful configs, as well as Kubernetes manifests, and applies the appropriate changes in Kubernetes to create, update, and destroy deployments. That was probably a bit abstract, so let me give you an example. A user creates a new post with a title and an image. For example, they post an image of a funny cat and title, "Hey, look at this cute cat," or funny cat. This event is now ingested into Snooron. And then the different workers in Snooron react to the events and any events emitted by those first workers. Since this post contains a text title, we perform various types of text classification on the title to classify it. Since the post also contains an image, we perform various types of image classification on the image. Since the post contains an image, we also perform OCR on the image to extract any embedded text, and then perform text classification on that extracted text. We further analyze the behavior of the user within this and other communities to identify bad or highly abnormal behavior. With the results of all of these analyses, we can then identify whether and what type of violations occurred. If a violation occurred, we can then choose the appropriate actions against the user and against the content, for example, to take down the content and/or ban the user. Finally, those selected content and user actions get applied. Each of these workers in the example I mentioned are separate workers and therefore also separate stateful functions. And they are also deployed as separate Kubernetes deployments. Now that we've gone through the high-level overview of the problems that we're facing and how we intend to solve it with our stream processing platform, let's now dive into the implementation in a bit more detail.
Let's talk a bit about our overall Flink Stateful Functions architecture, starting with our data ingestion piece. At Reddit, we process billions of internal analytics events daily. These events are fired off based on various pieces of activity across our site, such as when new posts or comments are created, when integrity scores are computed for pieces of content, and so on. These events are written to Kafka topics as raw JSON strings. However, in order to use these events within Flink Stateful Functions, as well as to have stronger typing, we want to convert these events into protobuf. How we do this is using a Java-based Flink embedded function that we've developed to convert this JSON to protobuf, implementing custom deserialization and serialization logic. This embedded function can be parameterized with input and output topics via a config. What this means is that the input topics are going to contain the raw JSON data, and the output topics are going to be one-to-one mapping of the input to the output, and they contain the corresponding protobuf data for those inputs. One thing to note is that the input and output topics can live on different Kafka clusters. So, for example, in our case, we consume a bunch of these analytics events that all reside on our data engineering team's Kafka cluster, and the output topics live on our own Kafka cluster belonging to the safety team. So looking at the overall architecture on the right, you could see that we have an input topic containing JSON data, and then we have a fleet of embedded functions that can scale very nicely horizontally that convert this JSON to protobuf. And then we have an egress topic containing the converted protobuf output. In this image, there's only one input topic and one output topic, but in practice, we have a bunch of different inputs that are processed, and then we output the corresponding protobuf to an output topic that maps one-to-one with the inputs. So continuing on with our overview of stateful architecture, we'll now talk a bit about workers. Workers are RPC endpoints that are triggered by content from the stream, and they perform arbitrary analysis on this content. For example, this could include things like scoring a comment for toxicity or performing sentiment analysis on some text. At their core, workers are pure functions. They take in an input message from the stream and some state as inputs. This state is managed by Flink via RocksDB. And workers are configured with various ingresses and egresses that map to different Kafka topics. This defines under which circumstances a worker will be triggered and where output messages will be emitted, if any. And unlike the JSON to protobuf converter that we talked about earlier, which is implemented as a Flink embedded function, where the business logic of the worker is co-located with the Flink processes, these workers are implemented as remote functions, in that they are totally isolated from the Flink workloads, and they can be scaled totally independently. What's really cool about workers is that they can be chained together to produce some complicated enrichment workloads. For example, on the bottom, you could see an analysis worker reading from an input topic and then outputting to an intermediate topic that is then consumed by another worker. An example of how these intermediate messages will look like is shown on the right with this example analysis schema. This contains a Reddit ID, a string, and a toxicity value, which is a double.
All workers are currently written in Python, and other languages will be supported in the future. At Reddit, we have a bootstrapping framework that provides generic, protocol-independent helpers for handling and observing RPC-style server applications. In order to provide first-class support for Snooron workers, we implemented our own stateful library, which wraps around the existing framework with additional helpers. This gives us observability, metrics collection, error handling, and tracing, among others, for free. For example, the worker will automatically emit metrics during successful or failed execution and handle errors with different strategies like drop or dead letter queue. Let's look at some code for a toy example. This is a spamminess worker. This spamminess worker reads content such as posts and comments from a stream, makes an API call to a spamminess service, which provides a spam likelihood score using a machine learning model, and the worker writes the response into a new stream. Downstream workers can now, for example, use this result to take action against content that have a high spam score. The workers are written as simple Python functions with the @worker annotation. The @worker annotation can be parameterized to determine the input type, state variables, namespace, and name of the stateful function. Within a worker, the stateful context is accessible using the helper function use stateful context variable. Finally, the entry point to the application can be generated using the make entry point helper, which by default will expose all stateful functions that were defined in the current scope, although this behavior can be customized. The workers are thoroughly tested with unit tests and integration tests. This is a sample unit test for the spamminess worker, where we are verifying the API call to the spamminess service in various scenarios using the mock functionality of Python's unit test package. And here is the integration test that makes the actual API call to the spamminess service to verify the correctness and the total time taken for the operation. As already mentioned, each of these workers can be scaled individually. And to see how the workers perform at large scales, we run performance tests. In order to verify such complex systems, we've developed an in-house test tool called Dynamic Message Producer that produces messages to Kafka, just like how there are real-time messages in production Kafka. It is developed using Locust, which is an open source load testing framework. The tool generates messages using a user-defined load profile, such as number of messages to be produced, frequency in which they need to be produced, and the number of users, therefore simulating user behavior. This diagram explains the end-to-end testing of a worker, the spamminess worker, for example. Given a specific load profile, the message producer produces messages to Kafka. The worker then processes these messages from Kafka ingress topic by calling the spamminess service and emits the spam scores for each of these messages to an egress topic. And for the verification, we verify the number of messages produced, the correctness of the scores, and the end-to-end time taken. Here is the code snippet for the same with a sample user input and the corresponding operations.
So how do we deploy our workers? There are three main processes that we need for a worker. First is the Flink master, and then we have the Flink worker, and finally, the remote function that contains the core business logic for the worker. All of these components are deployed and scaled via Kubernetes, and our deploy pipelines for production and staging are managed with Spinnaker, which we'll talk about in a bit. Our Flink processes are configured using a module.yaml file, which is common for Flink Stateful Functions applications. This module YAML specifies ingresses, egresses, and the function endpoint that should be triggered on each event that comes through the system. And we use Kubernetes config map to parameterize and mount the module YAML in each container. This module YAML is going to be unique per worker and per workload. Each component in the system, the Flink master, worker, and remote functions, can be are scaled independently, and this also provides the benefit for our stakeholders, who not all of whom are engineers. So they only have to worry about their core business logic in the remote function rather than concerning themselves with Flink internals. As you can see on the right, this is what a worker is comprised of. These three main pieces, and the Flink components are separated out into their own Kubernetes namespace, separately from the remote functions. First, we have our development environment, which is a sandbox Kubernetes environment where local changes are reflected. So if a developer makes a change locally, that change will be deployed immediately to the sandbox Kubernetes environment. This environment contains all the core pieces of a Flink stateful function, such as a Kafka broker, Zookeeper nodes, Flink, as well as the remote function itself. So at the end, this allows a developer to test one-off events from end-to-end processing. So they could, for example, write a message to a Kafka broker and observe that the stateful function is processing the message as expected. Next, in our staging environment, we have a more controlled production environment. So what this means is that messages are processed from test topics. So our worker will be reading from a test topic that can either contain one-off events that we write through, similar to our development environment, or even siphon production traffic to better load test before working out to 100%. And finally, in production, messages are read directly from production topics. So workers are handling the full traffic load.
We could have easily built out some of the real-time safety applications just for our team and forgone building a platform at all, or build a simpler platform just for our own use. However, the real value of this type of system comes from its use as a data rail by many teams. so that teams can easily own parts of a workflow and build on top of each other's work. As a result, we spent a significant amount of time on creating a good developer experience and on offering training to our users. So let me share a few of the things that we did. Firstly, we built out a template repo that contains working code for a sample worker with detailed inline comments explaining roughly what every single line of the example does. The template repo also has working unit, integration, and end-to-end tests, as well as fully configured tooling. Altogether, this enables users to get started with a working setup using just a single click. Secondly, we added detailed documentation in the README of the template repo outlining the repo structure, different ways of setting up the development environment, and how to use the different built-in tools. Thirdly, we included configuration for Visual Studio Code and its remote containers extension. Also known as dev container, the dev container config specifies a Docker image that is initialized as the development environment. The extension builds the container so that the same environment can easily get replicated on many different machines, as long as they're on Docker. The project is then mounted in the container. That in particular greatly reduced the complexity of getting started, in particular for some of our data scientists. Now, not everybody uses VS Code, and maybe not everybody even likes it. But in order to get started, it was really easy to use it with this extension. And once you know how to write a worker, you can then switch to your own preferred development workflow. Finally, we also hosted recorded training sessions with different teams, where we helped with answering any questions they had, and then in real time had all attendees set up a new project using the template repo. We then walked them through the code base and showed how everything worked, including running the actual worker and all the different tests. We answered any questions and then also helped resolve any issues they ran into, so that by the end of the workshop, everybody had a working local environment. Let me share some of the lessons learned from this. First of all, having a template repo or a similar way to easily get started is incredibly helpful. Documentation and developer tooling is as much, if not more important, than the actual features of your platform. You can always add more features later, but only when you add documentation and tooling, you empower your users to get started on their own. Creating documentation and building out developer tooling also forces you to clarify your own understanding of the problem space and to radically simplify your interfaces and workflows, since someone who is not on your team should be able to use it with minimal or no instruction and still get it to work. If I could go back in time and change one thing about how we approach this project, then I would probably say that I would focus on building out the examples, documentation, and tooling even sooner so that we could get our platform in the hands of our customers even sooner and get their feedback. We are still well on our way with our journey with Flink and with rolling out our own platform. Some of the use cases we're looking to target with the platform are identifying and taking action against spam, as already alluded to in the examples, slurs, and also against harmful bots. But there are many, many more. We're also looking to continuously improve our documentation and developer experience. So far, we've also primarily focused on Python, but we are looking to gradually add support for workers in other languages as well. Finally, we've so far been focused only on stream processing, but we're also interested in exploring Flink's model of a unified stream and batch processing system to further extend the platform. In this talk, we've shared how we use Flink Stateful Functions at Reddit, how we designed and implemented our own real-time stream processing system using StateFun, how we built on top of it to create a good developer experience, and finally, how we're rolling it out to other teams at Reddit. We hope that the learnings we've shared have been insightful, and we hope that they will help you with your own journey into stream processing and with Flink Stateful Functions. But we're still on our journey ourselves, and there's still lots more to be dreamed up and built. Reddit is expanding internationally, and we're hiring across all roles in all of our locations. Check out redditinc.com for open roles and to learn more. You can also reach out to me directly on LinkedIn if you want to have a chat. And with that, thanks for listening and or watching, and I'm now looking forward to all of your questions in the Q&A.